information, then in a very simple case, let us try to understand. Let us try to convert a simple NFA to DFA conversion. Okay, let us try to have a simple NFA to DFA conversion. We will be going with, we will be taking two examples here. Today we'll finish example 1. Okay, and I wish that you should do it with my with me also, so that you can understand. Okay, so you have a given. What is given? Example, you have a given. Given as given language L based on set of alphabet A and being defined by a regular expression, say A star. Then we need to convert. Then we say that define deterministic finite automata for the language L. Okay, so what is defining the language deterministic finite automata for language L? So now this is here. So what are given to us is regular expressions, say A star. So in simple case, once we have a regular expression, we need to have the possible set of words which can be generated using a regular expression. So this is A raised to n, where n goes from 0 to infinity. Okay, so this is one. Then what is important required is input symbols we need to define. So what is input symbol for us? Input symbol for us is A only. Fine. Okay. So then we have got a regular expression. This is our regular expression. So we called it as, okay, we called it as a regular expression. Okay. So once we have got a regular expression, let us go ahead here for drawing a non-deterministic automata. So we'll say my non-deterministic automata will be like this. So I can say this. The same non-deterministic finite automata which we have drawn earlier. So this is 0th state, this is state number 1, this is state number 2, this is state number 3. So here I have got A. From here I am moving with epsilon. From this I am moving here with epsilon. This is epsilon, this is epsilon. Okay, and here I need to designate a state as an accepting state. Okay, so the input symbol I have defined. Then with regular with this particular non-deterministic finite automata, I am trying to define what is my start state. Okay, so my start state is 0. My accepting state is here is 3. Is my accepting state. Okay, whether these these words are being prepared by this NFA, yes or no, we'll try to see. Like if we wanted to so let's validation whether it produces the same. Okay, in order to prepare epsilon, what is the path from 0 to 1, 1 to 3? So we'll say 0, 1, 1, 3. So I'm going to 3 is accepting state. So which means that epsilon, epsilon. So the epsilon, epsilon means null concatenated with null. You are getting null as output. Okay. So this in simple case, what is being generated? This is generated. Now, can I have 1 A's? So for just have a validation for 1 A. What you can do that you can go with 0 to 1, 1 to 2, 2 to 3. So 3 is your accepting state. So the path is in this case 0 to 1 is epsilon A epsilon. So null is concatenated with the alphabet A. So in this case null A null. So which is nothing but A only. Okay. So can I have 2 A's now? Multiple A's. Just for validation, it is say 0, 1, 2, 1, 2, 3. So 3 is my accepting state. So it is nothing but epsilon A, epsilon A, epsilon. So the output will be here, means two nulls are being concatenated. Null with A is A, with null is A only, with A is AA now. Here AA is being generated and done. So validation is also done. So means what? This NFA is going to be correct one. So whenever we are converting now, important points. Whenever we are converting NFA to DFA, the key pointers are we need to minimize epsilon transition state. So so means what? We are trying to minimize this epsilon transition states. Okay, means we need to remove the epsilon transition states. Edges we need to remove. Okay, so minimize the epsilon transition states, and at the same time, epsilon edges are minimized. Okay, and this is being done by subset generation, and this we are preparing by subsets generations. Okay, so in some of, if you refer back to the initial videos of finite automata, you will find that okay, how you can compute a transition function and how you can compute the states that we have done. Okay, so now let us go for step one is we will go with this particular solution into stepwise fashion. So we'll have step one. Step one is compute epsilon closure set of epsilon closure state of start state. Okay, epsilon closure state of start state. So we have to, means that we have to compute a closure state of 0. Closure set of 0. Closure set of 0 is containing 0, 0 to 1. 1 is reachable with epsilon input, and from 1, 3 is reachable with epsilon input. So my sets are 0, 1, and 3. Okay. So 0, 1, and 3. So these three states are there. So I am going to refer this as set A. So I don't have this set earlier with me, so it is 0, 1, and 3. So this is A. So once you have got a closure set, what you need to do is step number 2. Step 2. Okay. Then what you need to apply input symbol. Apply an input symbol on what? On closure set. Closure set and collect the state. Okay, and collect the state. So now what is our input symbol? Our input symbol is A. A is our input symbol. So now you can figure out on which state the A is being applied. Okay, so just to understand this, on which state A is applied, say on 0, what we have epsilon. Okay, on 0. On 1 we have A input. Now on 1 we have A input, so it is containing 0, 1, and 3. Okay, so it is, look at here, it is containing 0, 1, and 3. So on 0 I cannot apply A. It is on 0 it is epsilon. On 1 it is A. So 1 is leading to, so here if you look at this one, then this one is leading to a state called 2. So for me the answer is, say if I apply A with A. A means what? A means 0, 1, and 3. So out of this A, means out of the states that are present in A, I am searching for a state on which A is applied, and the answer is 2. Okay, so on which A is being applied. So answer is 2 only. So for this 2, I am again computing a closure state. So for closure state, it is 1, 2, and 3. Okay, collect the state and calculate closure set of the collected set. Collected. So what is collected? The result is B, result is 2, and 2's closure is 1, 2, 3. So okay, so do we have this state earlier defined? No, we don't have a earlier defined state. So we'll say that this is B. Okay, so then what is next? So we have got one more set here, A. So one more set is called B. So we will say like, okay, now once we have got B, okay, we have applied, we are going to apply a same input symbol. What is that? A. So okay, can we apply a same input symbol? Okay, let us try to have this. This is closure set. So can we have A as an input symbol here? Applied? Yes, that is 1, 2, and 3 only. So means what? In this B there is a state called 1. In this B there is a state called 1 where A is being applied, right? So where A is being applied. So again, this is going to give me the state number 2, and the closure of 2 is 1 comma 2 comma 3. So do we have this? Do we have a new set here? No, we have a same state. So let us try to say this as B only. Okay, so A with A is B and B with A is B only. Okay, so this is important. So once we have this, then we need to proceed this step to till. Important. This step to till no new sets are left. No new sets are left. Means whatever sets that we are generating, we are producing the words from that sets, and we need to do this process till no new sets are left. Okay, so this is important. So once we have this, then we need to step number 3. Once we finish with the step number 2, we need to go for step 3, right? Prepare transition table. Okay, we need to prepare a transition table here. Okay, so whenever we are preparing a transition table, we need to prepare a transition table with respect to input state. So this is the state and this is input alphabet A. A with the A is B and B with the A is B only. So here we can say, we can optimize that. Okay, A is equals to B. Means wherever B is coming, B is being substituted as A itself. Okay, so means the modified transition table for when I say B is equals to A, so means that wherever the B is coming, the modified transition table is now is becoming like this: A itself. Okay, so B is okay A. So here means what? Wherever B is there, B is being replaced by this. Okay, so once we have an optimized state, so look at here. Look at here means now here B is coming out of scope, right? Because A and B both are the set, both sets are same. So here we are going to draw a finite automata now, a deterministic finite automata, and deterministic finite automata is like this. A, and this is gonna be A. Okay, and do we have an accepting state here? Now look at here, 3 is here, 3 is here. So means what? The same uh, this is going to be my accepting state, and look at here. Okay, so this is my deterministic finite automata. Okay, so this is my DFA. Okay, now look at this. Can it be a null? Yes, it can be null. From this state, if I don't take this A as an input, then I am at accepting state only. So what is being generated? Epsilon is being generated. Now, can I have one A's? Yes, I can have. I can start with A, take this particular edge and come back to A and stop, which means that this will produce epsilon also, this will produce A also. Can this produce AA? So in case of AA, it is A. So means what? You are going for first A, take first A, come here, then take one more A, come here. So you have got two A states. Okay. Now can it be like A raised to N? Yes, you can have A raised to N. So simply by visiting A n number of times with AH. So this is going to be your deterministic finite automata, and you have converted this non-deterministic finite automata from look at here, from this you have converted to this. Okay, so here how many states are there? Here 0, 1, 2 and 3. Three states are here. Here how many states? One state. And this one state is leaving with only one edge, with only one symbol. Now here in case this 0 is leaving 0 with epsilon edge, right? Okay, if you look at 1 is leaving with A as an input, with epsilon as an input. So means what? You have two A's that are leaving to A, but both of them are with a different symbol. This is epsilon. Now if you look at this 2, then 2 is leaving and reaching to 3, but for 2, 1 is the epsilon, and from 2 to it is coming 1 with epsilon. So here the input symbols are common. Here we need not to bother about what input symbol that we are going to have. But in case of deterministic finite automata, I would like to bring in your notice that in this case, in case of this deterministic finite automata, look at here, you have only a vertex A, labeled vertex A, with only one edge, leaving with only one input symbol. So this is really very important. Now if you have any questions, you can come back to me, and